Some nights the sky feels like a question you forgot to ask. 2 points of light. One moves through darkness it will never escape. One moves through darkness it knows by heart. Maybe that's all astronomy ever was, watching strangers and neighbors trying to understand why both matter. Tonight we're going to listen to 2 visitors, not with ears but with something older, curiosity maybe, or that part of you that wonders what rocks remember when they drift for 1 billion years. Their names are 3I Atlas and 1999 KW4. One came from another star. One was born near ours. Both passed close enough for us to whisper back. Scientists call them small bodies, as if size were the point. As if a grain of sand from another shore meant nothing, because you could hold it in your palm. You don't need to understand everything tonight. Just let the silence do its work. Let the darkness feel a little less empty. Before we drift into their stories, though, if these quiet journeys feel like home to you, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more nights like this, and ring the little bell. Not for noise, but so the next quiet story can find you when you need it most. Now, let's drift. The first visitor arrived on a Tuesday, September 27th, 2024. Atlas Telescope in Hawaii. The one that watches for rocks that might end us caught something moving wrong. Not wrong like broken, wrong like foreign. Its path bent the wrong way. Most comets fall toward the sun, swing around, fall back out. Ellipses, loops. The grammar of orbits we've known since Kepler scribbled ratios by candlelight. This one didn't loop. It came in at 81 kilometers per second, faster than anything bound to our sun should move. Its trajectory curved once gently like a hand waving in passing and kept going. Scientists calculated backward, tracing the line into the past, and found it pointed toward Lyra, the constellation of the Harp. A coincidence maybe. The universe doesn't think in symbols, but humans do. They named it 3I Atlas. The I stands for interstellar. The third object we've ever confirmed came from beyond. The third stranger to pass through a neighborhood 4.5 billion years old. Its nucleus, the solid part. The memory frozen in ice is maybe 500 meters wide, about the length of 5 football fields. Small enough that if it grazed your planet's atmosphere, you'd call it a firework. Big enough that it carried chemistry from a place where our sun is just another anonymous spark. When they pointed spectrographs at it, instruments that split light into its component truths, they found water, frozen, carbon dioxide, hydrogen cyanide, methanol, the same molecules that swim in your cells that made the first RNA fold into the shape of wanting to continue. It had been cold for a very long time. Interstellar space sits at 3 Kelvin. That's negative 270 Celsius. Cold enough that atoms barely vibrate. Cold enough that time feels slower, if time were the kind of thing that could feel. Then it fell toward our sun and woke up. By December, it would reach perihelion closest approach, about 57 million kilometers out, closer than Mercury ever gets. Close enough that ice sublimates directly to gas, no liquid in between, and forms a coma. A cloud of vapor, 50,000 kilometers wide, glowing faintly in reflected sunlight. From Earth, it looked like a smudge. From itself, maybe it felt like exhaling after holding your breath for 1 million years. The second visitor we've known longer. May 20, 1999. Linear Survey, another telescope, another program scanning the sky for things that move, found an asteroid. Not unusual. We find asteroids the way beaches find sand, but this one came closer than most. They cataloged it 1999 KW4. The letters mean nothing except order. The year means when we noticed, not when it was born. It's a binary. 2 rocks held together by gravity, so weak you could escape it by jumping. The larger one, Alpha, stretches 1/300 meters across. The smaller Beta is 360 meters. Beta orbits Alpha every 17.4 hours, circling at a distance of 2.6 kilometers. Imagine 2 dancers in a ballroom with no floor, no walls, no music, just the faint tug of mass keeping them turning. Alpha spins fast, once every 2.8 hours. Fast enough that if you stood on its equator, if standing were possible in gravity, 1/10,000th of Earth's, you'd feel the surface trying to throw you into the dark. In May 2019, the pair swung past Earth. Not close enough to worry, 5.2 million kilometers, 13 times farther than the moon. But close enough that Arecibo, the great radio telescope in Puerto Rico, could bounce radar off them. Radar doesn't lie. It measures distance by counting seconds. It measures shape by watching how echoes shift. The images came back precise boulders the size of houses scattered across Alpha's surface. An equatorial ridge like a seam where two halves press together. Beta's face smoother locked to always watch Alpha tidally frozen in mutual gaze. Arecibo collapsed in 2020. Its cables snapped, its dish crumpled into the jungle, and the data it sent back became the last words of a language we're still learning to speak. But the asteroid didn't stop. It's out there now, somewhere in its ellipse, completing another lap. It will come close again in 2036. We'll listen then if we remember to. 2 visitors, 1 stranger, 1 neighbor. 1 will never return. 1 returns on schedule, patient as tides. Both are just rocks. Silicon, carbon, ice, metal. Atoms arranged by chance and time into shapes that hold no opinion about being observed. But you're listening to their stories anyway. Maybe that's the question the sky keeps asking. Not what they are, but why you care. Why humans spend billions to bounce light off stones. Why we name them, track them, wonder what they remember. Tonight we're going to answer that question, not with certainty. Certainty is the wrong tool for this kind of work. We'll answer it the way the night answers when you ask it to hold you, softly, slowly, by letting the silence matter as much as the sound. Interstellar space is not empty. You might think of it that way, void black, the absence of things, but it's full, just not with anything you'd recognize as company. Hydrogen atoms scattered so thin that a cubic meter holds maybe 1. Dust grains smaller than the particles in smoke drifting at speeds that would vaporize steel. Cosmic rays protons moving so fast, they carry the energy of a well-thrown baseball in a single subatomic point. And cold. Not the cold of winter. Not even the cold of liquid nitrogen. 3 Kelvin. That's the temperature of a universe still cooling from its own birth. At 3 Kelvin, molecules stop dancing. Electrons settle into their lowest energy states. Time, if it could shiver, would. This is where 3I Atlas lived. Not for years, not for millennia, for time scales that dwarf the existence of your species. It formed around a star we'll never name, in a disk of gas and dust, spinning in the dark. Ice is condensed. Carbon stuck to silicon, organic molecules. Those strange words like hydrogen cyanide and methanol froze into the matrix. Then something happened. Maybe a planet migrated inward its gravity, slinging smaller bodies outward like stones from a sling. Maybe the star had a companion, and the 2 stars' orbits sent debris scattering. Maybe nothing dramatic at all, just the slow accumulation of tiny gravitational nudges over 1,000,000 years until one day this particular chunk of ice found itself moving faster than escape velocity. It left. Scientists estimate it traveled for at least 4 million years, maybe longer. You can't carbon date a comet, can't count its rings like a tree. You can only calculate backward from its trajectory, measure its speed, and make educated guesses about where it started. The direction points toward Lyra. That's a region of sky about 25 light-years away. In that direction sit stars like Vega, bright young burning blue-white. But Vega's only 4.55 million years old. Too young to have formed rocky planets, let alone ejected them. So, the parent star is something else, something older, something we haven't named because it's too faint, too far, too ordinary. 3I, Atlas doesn't remember its sun. Memory requires chemistry that runs, not chemistry that's frozen. But when you warm it up, the chemistry wakes. September 27th, 2024. Larry Deno, an astronomer working with the Atlas survey, noticed something in the data stream, a moving dot. That's not unusual. Atlas finds asteroids the way rain finds pavement. But this dot had the wrong motion. Asteroids inside the solar system move in predictable ways. They're bound to the sun's gravity-tracing ellipses that repeat every few years or decades or centuries. You can calculate their orbits with the equations that fit on a napkin. Newton figured this out with a quill pen. This object wasn't following an ellipse. Its trajectory was hyperbolic. That's the mathematical term for a path that comes in once and leaves forever. The shape you get when your speed exceeds escape velocity, when you're not bound. Deno flagged it. Other telescopes confirmed it. Within 72 hours, scientists had calculated its orbital eccentricity, 1.03. Anything above 1.0 means you're not coming back. They ran the numbers backward. If you know where something is and how fast it's moving, you can trace its path into the past. The line pointed outward, away from the sun, away from the planets, away from the Kuiper belt and the Oort cloud, those distant reservoirs of icy bodies that mark the solar system's edge. It came from beyond. The name 3I Atlas is a catalog designation. The I means interstellar. The 3 means it's the third confirmed visitor. Before it came 1I Oumuamua in 2017, that strange cigar-shaped rock that tumbled through and sparked 1,000 theories. Then 2I Borisov in 2019, a comet so ordinary it almost felt reassuring. 3I Atlas is the third, not the last. We're getting better at spotting them. Telescopes sharper, surveys wider. Scientists estimate 1 or 2 interstellar objects pass through the inner solar system every year. Most go unnoticed, too faint, moving at the wrong angle, arriving when our instruments point elsewhere. But we saw this one. By October, it had brightened enough for spectroscopy. That's the trick where you split light into colors and read the chemical fingerprints hidden in the spectrum. Every molecule absorbs light at specific wavelengths. Water ice absorbs in the infrared. Carbon monoxide shows up as a dip in the ultraviolet. You can't touch a comet from 150 million kilometers away, but you can taste its light. Keck Observatory in Hawaii pointed its mirrors. So did the Very Large Telescope in Chile, 4 8-meter mirrors working together sharp enough to resolve the face of a coin on the moon. The spectrum came back familiar. Water. Frozen water, H2O, the same molecule that makes up 60% of your body. Carbon dioxide, CO2, the same gas you exhale. Hydrogen cyanide, HCN, toxic but essential, one of the building blocks of amino acids. Methanol, CH3OH, a simple alcohol that forms in cold molecular clouds. These are not exotic chemicals. They're the alphabet of organic chemistry. You find them in comets born around our sun. You find them in the icy moons of Jupiter. You find them in the vast clouds between stars where new solar systems condense. The surprise wasn't what 3I Atlas was made of. The surprise was that it was the same. That chemistry, it seems, follows the same rules everywhere. That a comet born in another star's disk looks, tastes, smells. If comets had scent like a comet born in ours. Maybe we're not as unique as we thought. Maybe the recipe for worlds is written in a language older than suns. As 3I Atlas fell closer to the sun, it started to change. At 3 Kelvin, ice is rock hard. Molecules don't move. But as sunlight warmed the nucleus slowly, degree by degree, the ices began to sublimate, not melt. There's no liquid phase in the vacuum of space. Solid goes directly to gas. Water vapor, carbon dioxide, cyanide, all lifting off the surface, carrying dust with them. This formed the coma, a cloud of gas and dust surrounding the nucleus, glowing faintly in reflected sunlight. By November, the coma stretched 50,000 kilometers across. That's nearly 4 times the diameter of Earth. From our perspective, it looked like a faint smudge. No tail, those only form when the solar wind pushes the coma into a stream. And 3I Atlas wasn't close enough yet for that. Just a soft glow like breath on a cold window. But inside that glow, something fascinating happened. As gas escaped the nucleus, it pushed. Not much, maybe 1/100% of the sun's gravitational pull, but enough to change the trajectory slightly. Scientists call this non-gravitational acceleration. It's how you can tell a comet from an asteroid. Asteroids are dead rock, but comets are alive in their own slow way, breathing out their substance, pushing themselves with their own exhalations. The acceleration measured about 0.0002 meters per second squared, barely anything. But over weeks it added up. The comet's path bent slightly a few thousand kilometers off the purely gravitational prediction. This meant something important: the nucleus was active. Not just a dead lump of ice wrapped in dust, but a body with volatile regions, patches where sunlight reached fresh ice, where geysers of vapor erupted and fell back in the weak gravity. Astronomers watched the light curve. That's the pattern of brightness over time. 3I Atlas brightened and dimmed every 6.8 hours. That's its rotation period, the time it takes to spin once. The brightness variations were strong. That suggests the nucleus is elongated, not spherical, maybe twice as long as it is wide. A potato shape tumbling end over end, each face catching sunlight in turn. You could almost picture it. A lumpy iceberg, 500 meters long, spinning in the dark, trailing a thin veil of its own substance, moving at 81 kilometers per second toward a perihelion it would reach in December. By then it would be 57 million kilometers from the sun, closer than Mercury, hot enough relatively speaking that the outgassing would peak, the coma would grow brighter, maybe a faint tail would form, and then it would leave. Its speed is too great. The sun's gravity bends its path, but can't capture it. After perihelion, 3I Atlas will swing outward past the orbits of Mars, Jupiter, Saturn. By 2026, it will cross Neptune's orbit. By 2030, it will be farther than Pluto. By 2050, it will be a light day away. A distance light takes 24 hours to cross. It will fade, not because it stops existing, but because it returns to the cold. The ices will freeze solid again. The outgassing will stop. The coma will dissipate. In a few centuries, it will be as cold as it was before 3 Kelvin, silent alone. And it will keep moving. In 4 million years, it might pass near another star. Maybe that star has planets. Maybe one of those planets has telescopes, and someone notices a faint dot moving the wrong way, and they give it a name in a language we'll never hear. Or maybe not. Space is very large. Stars are very far apart. The odds of a close encounter are slim. Most likely 3I Atlas will drift forever. Not lonely loneliness requires awareness, just drifting. A small body carrying chemistry from one shore of the galaxy toward no particular destination. But for a few months in 2024, we saw it. We split its light into colors and read its composition. We measured its speed and plotted its origin. We watched it wake from a cold older than mountains and wondered what it meant that the universe makes the same kinds of ice everywhere. Some scientists use the word pristine, as in 3I Atlas carries chemistry unchanged since its formation, as in it's a time capsule from another star's birth. But pristine isn't quite right. Cosmic rays struck it for millions of years, altering molecules atom by atom. Dust grains sandblasted its surface. It's been shaped by time, just very slowly. Maybe the better word is patient. It waited millions of years to be warm again, to breathe, to be seen. And now the warmth is fading. Gravity is a conversation held in silence. Two bodies any distance apart speak to each other through the fabric of space itself. The language has no words, only curvature. Mass bends space-time. Other masses feel the bending and respond. When the masses are small and closed, the conversation becomes intimate. 1999, KW4 is 2 rocks talking to each other this way. They've been talking for a very long time. Alpha. The larger one stretches 1,300 meters at its widest point. That's just over 4/5 of a mile. If you stood at one end, hypothetically in a spacesuit, in gravity so weak you'd need to tie yourself down, you could see the curvature. The horizon would be close, maybe 800 meters away before the rock's bulge hid the far side from view. Beta is smaller, 360 meters across, about the length of 3 football fields. It orbits Alpha at a distance of 2.6 kilometers, completing one loop every 17.4 hours. From Alpha's surface, Beta would hang in the sky like a companion moon. Not rising or setting, it's tidally locked, always showing the same face, but visible always there, a gray-brown presence against the black. From Beta's locked face, Alpha would fill half the sky. Enormous, unmoving, a horizon made of rock instead of atmosphere. Neither has atmosphere, neither has weather, but they have each other. The system was discovered on May 20, 1999 by the Linear Survey in New Mexico. Linear stands for Lincoln Near-Earth Asteroid Research, a program designed to find objects that cross Earth's orbit objects, that might someday pose a threat or, less dramatically, teach us something about how planets form. 1999, KWV-4 qualified on both counts. Its orbit is an ellipse like most asteroids. Perihelion, closest approach to the Sun, sits at 0.23 astronomical units. That's closer than Mercury. Aphelion, the far point, stretches out to 1.17 AU, just beyond Earth's orbit. It completes one full loop around the Sun every 188 days, just over 6 months. That's fast. Earth takes 365 days. Mars takes 687. But 1999 KW4 lives in the inner solar system, where orbits are tight and years are short. The orbit crosses Earth's path. That makes it an Apollo-class asteroid named after 1862, Apollo, the first of its kind discovered. There are thousands of Apollo asteroids now. Most will never come close to Earth. Space is large and orbital timing matters, but sometimes the timing aligns. May 25, 2019. 1999, KW4 passed within 5.2 million kilometers of Earth. That's about 13.5 times the distance to the Moon. Not close by everyday standards, but close enough for radar. Arecibo Observatory in Puerto Rico powered up its transmitter. The telescope's dish, 305 meters across, was the largest single-aperture radio telescope on Earth before it collapsed. It could do 2 things no other telescope could: listen to the faint whispers of pulsars halfway across the galaxy and shout at asteroids. Radar astronomy works like this. You send a pulse of radio waves toward an object. The waves travel at the speed of light. When they hit the object, some reflect back. You measure the time delay, how long the round trip took, and calculate the distance. You measure the frequency shift, how much the reflected waves change pitch, and calculate the velocity. But Arecibo could do more. It could send pulses fast enough to create images. The radar pulse traveled 5.2 million kilometers in about 17 seconds, hit the asteroid, bounced back in another 17 seconds. Total round trip 34 seconds. But during those 34 seconds, the asteroid rotated slightly. When you send many pulses over hours, you build up a map of the entire surface. The resolution was about 7.5 meters per pixel, sharp enough to see boulders, sharp enough to see the shape, not just the outline, but the topology, the ridges, the craters, the way Alpha's equator bulged outward as if something had pressed against it from inside. The images showed Alpha as a contact binary. That's the term for 2 lobes pressed together like a peanut or a snowman. One lobe measured roughly 800 meters, the other 700 meters, meeting at a narrow neck. Scientists think it formed through a gentle collision. 2 separate asteroids drifting in the early solar system, moving slow enough that when they touched, they stuck instead of shattering. Over millions of years, their mutual gravity pulled them into a more spherical shape, but the seam remained. Beta, the smaller one, told a different story. Its surface was smoother, fewer boulders, fewer craters. The radar images showed a shape that was more rounded, less lumpy. This suggested Beta was younger, not in age, but in the sense that its surface had been reworked. The leading theory involves something called the Yorp effect. It's an acronym: Yarkovsky, O'Keefe, Radzievsky, Paddock. 4 scientists who worked out the math of how sunlight can spin up an asteroid. Here's how it works. Sunlight hits the surface and warms it. The surface re-radiates that heat as infrared. If the asteroid has an irregular shape, the infrared photons leave from different angles, creating a tiny net torque. It's like a paddle wheel pushed by light. Over millions of years, the torque spins the asteroid faster and faster. Eventually, the rotation speed exceeds the strength of the asteroid's self-gravity. The equator starts to bulge. Rocks slide toward the equator. And if the spin gets fast enough, material lifts off entirely. That's how you make a binary. The parent body spins so fast it sheds mass from its equator. The shed material coalesces into a moonlet. The moonlet drifts outward to a stable orbit, and you have a system like 1999 KWO4. Beta is made of Alpha's equator. Pieces that once sat on the surface now orbiting a few kilometers away, locked in a gravitational waltz. The orbit itself is remarkable for its stability. At 6 kilometers separation. Beta experiences tidal forces, the difference in Alpha's gravitational pull between Beta's near side and far side. Those forces are tiny, but over time they slow Beta's rotation until it becomes tidally locked. Now, Beta rotates once per orbit 17.4 hours. One face always points toward Alpha. The other face always points away toward the stars. From Beta's Alpha-facing side, you'd never see Earth. Never see the sun rise or set over Alpha's horizon. Just Alpha filling the sky unchanging, except for the slow march of shadows as Alpha rotates beneath you every 2.8 hours. From Beta's far side, you'd never see Alpha. Just stars. Unchanging stars because Beta doesn't tumble. No day-night cycle, no variation. Just the silent geometry of a universe held in place by invisible threads. The system's age is harder to pin down. The asteroids themselves are 4.5 billion years old. They condensed from the solar nebula when the sun was still a newborn. But the binary configuration is younger. Estimates suggest Beta separated from Alpha maybe 100,000 years ago, maybe a million. The uncertainty is large because the URP effect depends on shape, and shape changes over time as impacts reshape the surface. But compared to the solar system's age, it's recent. If the solar system's history were a 24-hour day, 1999 KW4 became a binary in the last second before midnight. Radar observations also revealed composition clues. The reflectivity, how much radio energy bounced back, matched S-type asteroids. That's a classification based on spectroscopy. S stands for silicaceous, meaning rock rich in silicon and oxygen, basically stone. S-types are common in the inner asteroid belt. They are thought to resemble ordinary chondrite meteorites, the kind that fall to Earth most often. The composition is roughly 90% silicate minerals, 10% iron, nickel, metal, some olivine, some pyroxene, some plagioclase, feldspar. The same minerals that make up basalt and granite, just mixed differently. If you could touch 1999 KW4, it would feel like stone. Rough, maybe, dusty, certainly. The surface is covered in regolith fine grains, pulverized by billions of years of micrometeorite impacts. But stone nonetheless. Not ice like a comet. Not metal like some asteroids. Stone like the rocks at your feet, but older. Arecibo made detailed maps during the 2019 flyby. The data-filled hard drives, hundreds of images each one, a snapshot of the surface from a slightly different angle. Scientists combined them into 3D models. The models showed boulders scattered across Alpha's surface, some as large as houses, 50 meters across. These weren't placed by any process. They were remnants, pieces that hadn't been pulverized yet, or fragments from impacts that landed gently enough to stay intact. The equatorial ridge on Alpha stood out clearly. It ran around the asteroid's middle like a belt rising maybe 50 meters above the average surface. Scientists think it's a gravitational feature material that migrated to the equator when Alpha was spinning faster before Beta separated. Beta's surface, in contrast, showed fewer large boulders, more uniform texture. This fits the theory that Beta is made of material that lifted off Alpha's surface smaller grains already partially pulverized that aggregated in orbit. Between Alpha and Beta, the space is not quite empty. There's a faint dust ring particles too small to form into a third body drifting in the gravitational equilibrium between the two rocks. Spacecraft haven't visited 1999 KW4. Everything we know comes from light. Reflected sunlight tells us about surface brightness. Radar tells us about shape and distance. Spectroscopy tells us about composition. But no camera has photographed it up close. No lander has touched its surface. Yet, we know it intimately. We know its orbit to within meters. We know its rotation to within seconds. We know the shape of its boulders, the angle of its ridges, the way its moonlet hangs in perpetual attendance. Arecibo collapsed on December 1st, 2020. The support cables failed. The instrument platform, 900 tons of metal suspended above the dish, crashed into the reflector, tearing a hole, ending 57 years of observation. The data it collected remains. Hundreds of terabytes. Maps of asteroids, spectra of pulsars, searches for extraterrestrial signals. The archive sits on servers accessible to anyone with the patience to learn its language. 1999, KW4 will return. Its orbit is stable, predictable. The next close approach happens in 2036, about 7.5 million kilometers, a bit farther than 2019, but still close enough for radar. Goldstone Observatory in California will be ready. So will the Green Bank Telescope in West Virginia. They'll send pulses, collect echoes, update the maps. By then, maybe there will be new telescopes. Maybe a spacecraft will visit drifting close enough to touch. Maybe humans will stand on Alpha's surface feeling gravity so weak they'd have to anchor themselves, looking up at Beta hanging overhead like a second horizon. Or maybe not. Space is expensive. Priorities shift. But the asteroid doesn't care whether we visit. It will keep orbiting the sun, Beta circling Alpha, the two locked in their quiet conversation. They've been talking for 100,000 years. They'll keep talking for millions more until a collision disrupts them, or tidal forces from a planetary flyby pull them apart. For now, they're stable, predictable. A neighbor we know by name, whose schedule we've memorized, who returns on time and without fanfare. Some nights, if you know where to look, you can see them. Not with your eyes, they're too faint too far. But with a backyard telescope under dark skies, they appear as a single point of light moving against the stars. One point, two bodies. A conversation held in gravity's silent grammar. Stars are born in clouds. Not the kind you see from your window, but clouds vast enough to birth 1,000 suns. Molecular clouds, regions of space where hydrogen gas thickens, where temperatures drop to 10 Kelvin. Where gravity starts to win against the pressure that keeps gas diffuse. These clouds span light years. Inside them, turbulence creates pockets of higher density. The pockets collapse. As they collapse, they heat. As they heat, they spin. The spinning flattens them into disks. And at the center of each disk, if conditions align, a star ignites. The disk doesn't disappear. It lingers orbiting the newborn star, cooling slowly. Dust grains silicates carbons. Ices stick together through static charge and gentle collisions. Millimeter by millimeter, they grow. Pebbles form, boulders form, planetesimals form. This is how solar systems begin. Not with intention, just with gravity and time. 3i, Atlas was born this way. Not here, not around our sun. Around a star we'll never visit in a disk. We'll never see 4.5 billion years ago, when the universe was younger, and our own solar system hadn't yet learned its current shape. Scientists estimate the parent star sits somewhere in the direction of Lyra, about 25 light-years away. That's close cosmically speaking. Close enough that the light leaving that star tonight will reach Earth around the time your great-great-great-grandchildren's great-great-great-grandchildren retire, assuming anyone's still counting generations by then. But the star itself is anonymous, too faint to have a catalog number anyone remembers, too ordinary to warrant a name. Just another G-type or K-type star, yellow or orange. Stable middle-aged burning hydrogen into helium, surrounded by whatever planets manage to coalesce from its disk. In that disk in the outer regions where temperatures never rose above 40 Kelvin, ice is condensed. Water ice, carbon dioxide ice, methane, ammonia, and more complex molecules, hydrogen cyanide, methanol, formaldehyde. The chemistry of cold. These molecules didn't form in the disk. They formed earlier in the molecular cloud before the star ignited. The disk inherited them, preserved them, locked them into grains that stuck together into pebbles, pebbles into comets. 3I Atlas was one of those comets. A small body maybe a kilometer across, originally orbiting its star in the cold dark beyond the snow line, the distance where water stays frozen. It might have stayed there forever. Most comets do. They orbit quietly, unchanged witnesses to nothing. But something disturbed it. Maybe a planet migrated. Gas giants don't always stay where they form. Gravitational interactions with the disk or with other planets can push them inward or outward. As they move, their gravity reshuffles everything nearby. Small bodies get flung into new orbits. Some fall toward the star. Some get ejected entirely. Or maybe the star had a companion. Many stars are born in pairs or clusters. If a neighboring star passed close within a light year or two, its gravity could perturb the outer comets, sending them on trajectories that don't return. Or maybe nothing dramatic happened at all. Just the slow accumulation of gravitational nudges. A near miss with another comet here. A resonance with a distant planet there. Over 1 million years, the orbit stretched eccentricity grew, and one day, 3I Atlas found itself moving too fast to stay bound. The star let it go. Not willingly, stars don't will. Just through mathematics. The trajectory became hyperbolic. The comet crossed the boundary between bound and free, and it kept going. For 4 million years, maybe longer, it drifted through interstellar space. No sunlight, no warmth. Just the faint glow of distant stars and the cosmic microwave background. The afterglow of the Big Bang cooled now to 2.7 Kelvin. Cosmic rays struck it. High-energy protons accelerated by supernovae, or active galactic nuclei, moving at nearly the speed of light. Each impact altered a few molecules, broke chemical bonds, created free radicals. Over millions of years, the surface chemistry changed, darkened, became something no laboratory has perfectly replicated. Dust grains hit it. Interstellar dust moving at tens of kilometers per second relative to the comet, each grain smaller than a bacterium, but carrying kinetic energy. The impact sandblasted the surface micron by micron, eroding features, smoothing craters that might have existed, carving new textures. And it stayed cold, 3 Kelvin. Cold enough that molecular motion nearly stops. Cold enough that time in a chemical sense freezes. Then, in September 2024, it entered our solar system. The sun's gravity bent its path. Sunlight began to warm it. The ices woke. 1999 KW4 has a different origin. Same age, 4.5 billion years, but different nursery. It formed in our solar system's asteroid belt, the region between Mars and Jupiter, where rocky debris never coalesced into a planet. The belt sits at about 2 to 3.5 astronomical units from the sun. At that distance, water stays frozen, but silicate minerals stay solid. The early solar system was chaos. Planetesimals bodies ranging from meters to hundreds of kilometers across collided constantly. Some collisions built planets. Earth grew this way, accreting mass through impacts over tens of millions of years. So did Mars, Venus, Mercury. But in the asteroid belt, Jupiter's gravity prevented coalescence. The belt's total mass is only 4% of the Moon's mass. Not enough to form a planet. Just enough to form a billion fragments. 1999. KW4's parent bodies formed in this environment. The leading theory suggests Alpha started as two separate asteroids, each a few hundred meters across, drifting on similar orbits. Over time, gravitational interactions with Jupiter and the other planets nudged the orbits closer. Eventually, they touched, not in a violent collision those shatter rock, in a gentle one. Relative velocity maybe a few meters per second, slow enough that instead of breaking apart, they stuck together through their mutual gravity and perhaps some friction from surface regolith. This created the contact binary structure we see today. Two lobes pressed together at a narrow neck, rotating as a single body. Beta came later, much later. As Alpha orbited the Sun, it absorbed sunlight. The sunlight warmed the surface. The surface re-radiated heat. Because Alpha has an irregular shape, the heat didn't radiate symmetrically. More heat left from some faces than others. The imbalance created torque. This is the Yorp effect. Sunlight over millions of years spun Alpha faster. At some point, estimates suggest 100,000 to a million years ago, Alpha's rotation period dropped below a critical threshold. The centrifugal force at the equator exceeded the gravitational force holding material down. Rocks began to slide toward the equator. Dust lifted off. Small boulders tumbled into orbit. Most of the ejected material fell back, but some reached a stable orbit just beyond the Roche, limit the distance where tidal forces balance self-gravity. That material aggregated into beta. Beta is made of Alpha's skin, regolith grains, small rocks, material that once sat on Alpha's surface baking in sunlight, cooling in shadow, now orbiting a few kilometers away. The separation happened recently, cosmically speaking. If the solar system's 4.5 billion year history were compressed into 1 year, Beta separated from Alpha sometime in the last hour of December 31st. Since then, tidal forces have slowed Beta's rotation. Now it's locked, one face perpetually toward Alpha, one face perpetually away. The two bodies' compositions are nearly identical because they share a parent, S-type spectra, silicate-rich, ordinary chondrite analog, the same minerals that make up most of Earth's crust, feldspar, pyroxene, olivine, just without the weathering, without the water, without the biology that transforms bare rock into soil. If you could stand on Alpha's surface and pick up a stone, it might look like basalt, gray-brown, fine-grained in some places, coarser in others. No crystals large enough to see this rock never melted, never recrystallized. It's primordial, dust compressed by gravity into stone, unchanged since the solar nebula cooled. But unlike Earth rocks, it would be bone dry. No water of hydration in the minerals, no clay, no rust, just anhydrous silicates and a scatter of iron-nickel metal grains. The iron came from the supernova that seeded our molecular cloud. Stars heavier than about 8 solar masses end their lives in explosions that forge elements heavier than iron. The blast wave compresses nearby gas, triggering new star formation. Our sun and everything that orbits it contains atoms born in a star that died before our sun ignited. So does 3I Atlas. Its parent star formed the same way from a cloud enriched by ancient supernovae. The iron in its ices, the carbon in its organics, all forged in stellar cores, expelled in death, recycled into new beginnings. Both visitors carry this inheritance. Atoms older than their stars. Atoms that remember in the arrangement of their nuclei the temperatures and pressures of environments no human will ever witness. The difference is journey. 3I Atlas wandered. 1999, KW4 stayed. 3I, Atlas saw. Another sun felt another star's warmth, then spent millions of years in cold so deep that entropy almost paused. It crossed the space between stars, a space where galaxies are visible, but individual stars blur into a faint collective glow. 1999, KW4 never left. It orbited the sun for 4.5 billion years. The same sun, the same light. It watched in whatever sense rocks can watch as planets formed and migrated, as Earth cooled and oceans condensed, as life began and evolved and built telescopes to look outward. Two births, same laws of physics, same chemistry, same age, but one remembers a star we'll never know. One remembers only ours. When scientists talk about origins, they often use the word pristine, as in asteroids and comets preserve the conditions of the early solar system. As in, they haven't been melted or differentiated like planets. But pristine is relative. Both visitors have been altered. 3I's, Atlas by cosmic rays and interstellar dust. 1999, KW4 by solar radiation and micrometeorite bombardment. What remains pristine is the bulk composition, the ratios of elements, the isotopic signatures. These don't change easily. They're fingerprints of formation conditions. In 3I Atlas's ice scientists found isotope ratios consistent with formation at very low temperatures below 40 Kelvin. That tells you about the disk it formed in, how far from its star, how cold the chemistry. In 1999, KW4's rock, the oxygen isotope ratios match ordinary chondrite meteorites. That tells you it formed in the inner solar system, where temperatures allowed silicates to condense but kept volatiles as vapor. Different stories, same grammar, gravity, temperature, time. You could think of them as relatives separated at birth. Same atomic ancestry supernova, ejecta compressed into molecular clouds. Same age formed within a few million years of each other. Same material, rock, ice, metal, organics. But they grew up in different homes, one in a system we'll never see, one in ours. And now, for a brief moment, their paths crossed. 3I Atlas passing through. 1999, KW4 circling back. Two stories that began in clouds continued in darkness and intersected here in this particular orbit, in this particular century, where telescopes waited to translate their light into understanding. Maybe birth doesn't define a thing. Maybe journey does, or maybe both matter. Where you started, where you went, where you are now, in the long pause between departure and arrival. Chemistry is a language written in bonds. Every molecule tells you something about where it formed, the temperature, the pressure, whether light was present, whether radiation broke things apart, or cold held them together. You can read a comet the way you'd read a diary if you know the grammar. 3I Atlas carries water. Not liquid. There's no liquid in space, not at these temperatures. Ice. Solid H2O frozen into a matrix with dust grains and other molecules. Scientists estimate the nucleus is about 20% ice by mass, maybe more. The rest is rock and carbon. When they pointed spectrographs at the coma, the cloud of vapor surrounding the nucleus, they saw the signature of water sublimating, not evaporating. Sublimation is solid to gas-skipping liquid entirely. At low pressure, that's how ice behaves. One moment, solid, the next vapor. The water isn't pure, it never is. Dissolved in the ice or mixed at the molecular level are other volatiles. Carbon dioxide. That's CO2, the same molecule you exhale, the same molecule melting from Mars's polar caps each spring. Carbon monoxide, CO. Methane, CH4. Ammonia, NH3, and organics. Hydrogen cyanide, HCN. Methanol, CH3H. Formaldehyde, H2CO. These aren't exotic. They're common in cold molecular clouds, the places where stars form. They're the alphabet of prebiotic chemistry. Hydrogen cyanide is particularly interesting. It's toxic to you. Yes, disrupts cellular respiration, binds to the enzymes that let your cells use oxygen. But in the right conditions, HCN polymerizes into adenine, one of the nucleotide bases in DNA and RNA. Life's recipe includes ingredients that, in isolation, would kill you. Methanol is a simple alcohol. 1 carbon, 1 oxygen, 4 hydrogens. It forms when carbon monoxide meets hydrogen atoms on the surface of coal dust grains. The grains act as catalysts. Atoms stick, meet, bond. Over millions of years, the surfaces of dust grains become coated in thin films of organic molecules. 3I, Atlas's ice, likely formed this way, in its parent star's protoplanetary disk, or even earlier in the molecular cloud before the star ignited. The molecules froze onto grains. The grains stuck together. The aggregates grew into planetesimals. One of those planetesimals became a comet. The isotope ratios matter. Isotopes are atoms of the same element with different numbers of neutrons. Hydrogen has 2 stable isotopes, protium, 1 proton, no neutrons, and deuterium, 1 proton, 1 neutron. Deuterium is heavier. It behaves slightly differently in chemical reactions. In 3I Atlas's water, the ratio of deuterium to protium is about 1 in 5,000. That's higher than in Earth's oceans, where the ratio is about 1 in 6,400. Higher ratios suggest formation at very low temperatures below 30 Kelvin, where deuterium preferentially bonds into molecules. This tells you the ice is old. Pristine in the sense that it hasn't been melted and refrozen. The chemistry locked in when temperatures were so low that molecular motion nearly stopped. Carbon also has isotopes, carbon-12 and carbon-13. The ratio of C13 to C12 in 3I Atlas's organics matches what you'd expect from cold chemistry, not the ratios you see in living organisms which preferentially use C12. Not the ratios you see in Earth's atmosphere influenced by billions of years of photosynthesis and respiration. Just the baseline, the ratio that forms when carbon and oxygen and hydrogen meet in the dark. 1999 KW4 carries different chemistry. It's an S-type asteroid. S for silicaceous. That means rock rich in silicon and oxygen silicate minerals, the kind of rock that makes up Earth's mantle and crust. Olivine pyroxene plagioclase feldspar. Olivine is McFay 2SiO4, magnesium or iron silicon and oxygen arranged in a crystal lattice. It's greenish when pure, though you'd never see the color on an asteroid space weathering darkened surfaces over time. Olivine forms at high temperatures above 1200 Kelvin. It condenses directly from vapor in a cooling protoplanetary disk. Pyroxene is similar but structurally different, MgFe SiO3. Chains of silica tetrahedra instead of isolated units. It forms at slightly lower temperatures than olivine, around 1000 to 1200 Kelvin. These minerals tell you 1999 KW4 formed in the inner solar system inside the snowline. The snowline is the distance from the sun where water stays frozen. Inside it, temperatures are too high for ice. Only rock and metal condense. Outside it, ices dominate. The asteroid belt straddles the snowline. The inner belt is rocky. The outer belt is icy. 1999, KW4 sits in the inner belt, or at least it did before gravitational interactions nudged it into an Earth-crossing orbit. The rock is dry. Spectroscopy shows no water of hydration, no OH bonds in the mineral structure, no clay minerals which form when water alters rock, just anhydrous silicates, bone dry. There's also metal, iron-nickel alloy scattered through the rock in grains a few micrometers to a few millimeters across. The metal condensed early in the solar nebula when temperatures were high enough to vaporize iron, but cool enough for it to solidify into droplets. The iron came from a supernova, every atom heavier than helium did. Stars fuse hydrogen into helium-helium into carbon, and oxygen into heavier elements. But fusion stops at iron. Iron 56 is the most stable nucleus. Fusing it costs energy instead of releasing it. Stars can't do that and survive. So heavier elements, cobalt, nickel, copper, zinc, all the way up to uranium form in supernovae explosions. The blast wave compresses nuclei together, forcing them to merge despite the energy cost. The explosion then scatters these elements into space. Our solar system's iron and 1999 KW4's iron, condensed from gas enriched by at least one supernova, maybe several. The atoms in the asteroid are older than the sun. They remember temperatures and pressures that would atomize any laboratory. 3I Atlas's carbon remembers too. Carbon in organic molecules. Carbon that was once inside a star fused from helium, expelled in a stellar wind, or a supernova incorporated into a molecular cloud, frozen into a comet. The same carbon that makes up your cells. The same carbon in the graphite of a pencil, the diamond in a ring, the CO2 you exhale. Carbon is promiscuous. It bonds with almost anything. 4 valence electrons ready to share. In 3I Atlas carbon bonds with hydrogen to make methane and methanol, with oxygen to make carbon monoxide and dioxide, with nitrogen to make hydrogen cyanide, with sulfur to make carbonyl sulfide. Each bond is a sentence in the story of where the molecule formed. Scientists sometimes call comets dirty snowballs. It's a cute phrase, but it undersells the complexity. A comet isn't just ice and dust. It's a library, a record of conditions in another star's disk, preserved by cold delivered to us by chance. When 3I Atlas warms near our sun, the ices sublimate. The molecules enter the coma. Solar ultraviolet light breaks some of them apart. Parent molecules fragment into daughter molecules. Water breaks into OH and H. Methanol breaks into CO and H2. The fragments emit light at specific wavelengths, and we measure those wavelengths with spectrographs. From the fragment ratios, you can work backward to the parent composition. It's detective work. The crime is 4 billion years old. The evidence is light. 1999. KW4's rock doesn't sublimate. It's solid at any temperature the sun can throw at it. But it's not unchanged. Solar wind hits the surface. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the sun at 400 kilometers per second. When these particles hit rock, they sputter atoms off the surface, literally knock them free. Over millions of years, sputtering erodes the surface. It also creates amorphous layers, regions where the crystal structure is disrupted, turned glassy. This darkens the rock. Fresh olivine is greenish. Space-weathered olivine is nearly black. Micrometeorites hit too. Tiny grains of dust smaller than sand moving at tens of kilometers per second. Each impact melts a microscopic amount of rock, creating tiny glass beads. The beads accumulate. The surface becomes a mix of rock glass and metal, all pulverized into dust, so fine it behaves almost like a fluid. This is regolith. Not soil requires organic matter biology. Regolith is just broken rock. On 1999 KW4, it's tens of meters deep in places, maybe 100, deep enough to bury a building. If you scooped up a handful hypothetically in a spacesuit in microgravity, it would feel like flour, fine dry, clinging to your glove by static charge. If you looked closely, you'd see fragments of olivine pyroxene metal, maybe a few glass spherules catching light. No water, no organics, just rock and time. The contrast between the two visitors is stark. One carries ice and organics, the chemical building blocks of life. One carries rock and metal, the structural elements of planets. But both carry memory. 3I Atlas remembers cold. Temperatures where molecules stop moving, where chemistry freezes mid-reaction. 1999 KWV4 remembers heat. Temperatures where rock condenses from vapor, where metal melts and solidifies. One remembers another star's light. One remembers only the sun. You could say they're opposites. Ice versus rock, organic versus mineral, volatile versus refractory. But they're also complements. You need both to make a world. Earth has a rocky core, an iron center water. Ocean's an organic biosphere. It's built from materials like 1999 KW4 and materials like 3I Atlas. Maybe every planet is. Maybe you can't have one without the other. Rock to hold the shape, ice to bring the chemistry, metal to anchor the core, organics to start the conversation that becomes life. If you could gather every comet and every asteroid in the solar system and compress them into a sphere, you'd get something like a planet. Not habitable, not yet, but the raw ingredients, the alphabet. 3I Atlas and 1999 KW4 are two letters, written in different scripts, pronounced differently, but part of the same language, the language that writes worlds. Everything moves, even things that seem still. Mountains, oceans, continents are drifting. Plates shift millimeters per year. The ground beneath your feet is traveling at hundreds of meters per second as Earth rotates. Earth itself orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at 220 kilometers per second. Stillness is an illusion. Motion is the default state of matter. 3I Atlas moves like nothing bound to our Sun can move. Its velocity relative to the solar system's center of mass is 81 kilometers per second. That's fast. Fast enough to cross the distance from New York to Los Angeles in less than a minute. Fast enough that if you were standing still in space and it passed, it would be over the horizon before you could finish blinking. But it's not just the speed, it's the direction, the trajectory. Most objects in the solar system move in ellipses, closed curves. They fall toward the Sun, swing around, fall back out, repeat. The mathematics are elegant. Kepler worked them out with a quill pen in the 1600s. Newton explained why with gravity. Einstein refined it with space-time curvature. But the basic shape remains ellipse. 3I's Atlas doesn't follow an ellipse. It follows a hyperbola. A hyperbola is an open curve. It comes in from infinity, bends around a focus, in this case the Sun, and heads back out toward infinity. It never closes. It never repeats. The orbital eccentricity tells you which shape you're looking at. Eccentricity is a number between 0 and infinity. 0 means a perfect circle. Between 0 and 1 means an ellipse. Exactly 1 means a parabola. The boundary case between bound and unbound. Anything above 1 means a hyperbola. 3I Atlas has an eccentricity of 1.03. That extra 0.03 means everything. It means the comet is moving 3% faster than escape velocity. It means the Sun's gravity bends its path, but can't capture it. It means 3I Atlas is just passing through. The closest it gets to the Sun, perihelion, is 0.38 astronomical units. That's 57 million kilometers, about 38% of the distance from Earth to the Sun. Closer than Mercury ever gets, hot enough that surface ices sublimate rapidly, creating the coma. At perihelion, the comet's velocity peaks, about 91 kilometers per second, faster than it was when it entered the inner solar system. Gravity accelerated it on the way in, like a ball rolling downhill. After perihelion, it climbs back out. The Sun's gravity decelerates it, but not enough to stop it. By the time it crosses Neptune's orbit in 2026, it will have slowed to about 26 kilometers per second. By the time it reaches the heliopause, the boundary where the solar wind gives way to interstellar medium, it will be moving at roughly its original 81 kilometers per second. Then it will keep going, out past the Oort cloud, past the gravitational influence of the Sun, back into the space between stars. But here's the thing. It's not moving in a straight line relative to the galaxy. The Sun is orbiting the galactic center. 3I Atlas entered the solar system from one direction and will leave in another. But from the galaxy's perspective, both the comet and the Sun are moving in long, slow arcs around a common center. The comet's velocity relative to the local standard of rest, the average motion of nearby stars, is different from its velocity relative to the Sun. When you subtract the sun's motion, 3i Atlas is moving at about 30 kilometers per second through the galaxy. Slower than you'd think, typical for stars and interstellar objects in this region of the Milky Way. It's not fleeing, it's drifting, has been for millions of years, will continue for millions more. As it moves, it also tumbles. The light curve, the pattern of brightness over time, shows variations every 6.8 hours. That's the rotation period. The comet spins once every 8 hours, and because its shape is irregular, different faces catch sunlight at different angles, causing the brightness to rise and fall. The rotation isn't stable, as ice's sublimate gas escapes preferentially from certain regions. The escaping gas creates tiny jets, plumes of vapor shooting off the surface at speeds of a few hundred meters per second. These jets act like thrusters. They push the nucleus, altering its spin. Over weeks, the rotation period can change by minutes. Over months, the orientation of the spin axis can shift. This is why predicting cometary behavior is hard. They're not inert. They're active breathing, changing as they warm. The non-gravitational acceleration measured for 3i Atlas is about 0.002 meters per second squared. Tiny. But over weeks, it adds up to kilometers. Over months, tens of kilometers. Enough to make the trajectory deviate from a purely gravitational path. Scientists account for this in their models. They measure the comet's position over time, fit a curve, include terms for outgassing thrust, and refine the predictions. The current model says 3i Atlas will exit the solar system on a trajectory pointing toward the constellation Telescopium. Not because it's aiming there, comets don't aim, but because that's where the math says it's going. In a million years, it might pass near another star. Or not. Space is large, stars are rare. The odds are against close encounters. 1999 KW4 moves differently. Its orbit is an ellipse tightly bound to the Sun. Perihelion at 0.23 AU, closer to the Sun than 3i Atlas gets. Aphelion at 1.17 AU, just beyond Earth's orbit. The ellipse is moderately eccentricity, 0.69. Not circular, but not extreme. The orbital period is 188 days, just over 6 months, fast because the orbit is small and the Sun's gravity is strong. At perihelion, the asteroid's velocity is 48 kilometers per second. At aphelion, it slows to 27 kilometers per second. The variation is Kepler's second law in action. An object sweeps out equal areas in equal times, which means it moves faster when closer to the focus. The orbit crosses Earth's path. That's what makes 1999 KW4 a near-Earth object. The two orbits intersect, but intersection doesn't mean collision. It depends on timing. Where Earth is when the asteroid crosses. Most of the time they're on opposite sides of the Sun. Occasionally they're close. May 2019 was close. 5.2 million kilometers. Not threatening. Not even particularly close by astronomical standards, but close enough for radar. The orbit also precesses. Precession is when the ellipse itself rotates slowly over time. The long axis, the line from perihelion to aphelion, shifts its orientation. For 1999 KW4, the precession is caused mostly by gravitational perturbations from Jupiter and Earth. Each time the asteroid passes near Earth, Earth's gravity tugs on it, slightly changing the orbit by fractions of a percent. Over centuries, those fractions add up. The orbit evolves. Not chaotically, it's predictable, at least for the next few thousand years. But it drifts. Perihelion might shift inward or outward by a few hundredths of an AU. The orbital period might lengthen or shorten by days. Eventually, one of three things will happen. The asteroid might collide with Earth, or Venus, or Mercury, or it might be ejected from the inner solar system by a close encounter with Jupiter, or it might settle into a more stable orbit and stay there for billions of years. We don't know which. The orbit is chaotic on long time scales. You can predict the next 1,000 years with reasonable confidence. The next million is guesswork, but for now, it's stable, predictable. It returns every 188 days regular as a clock. While it orbits, it also spins. Alpha. The larger component rotates once every 2.8 hours. That's fast. Fast enough that material at the equator feels significant centrifugal force about 1/3 of the already weak surface gravity. This is why Alpha has an equatorial ridge. The ridge is a band of material that migrated to the equator when the asteroid was spinning even faster before Beta separated. As the Yorp effect spun Alpha up, rocks slid downhill toward the equator, accumulating in a bulge. Now the spin has slowed slightly. Beta's formation removed angular momentum from the system. The tidal interaction between Alpha and Beta continues to transfer angular momentum, gradually slowing Alpha's rotation and pushing Beta's orbit slightly farther out. In a few 100,000 years, Alpha might rotate once every 3 hours instead of 2.8. Beta's orbit might expand to 3 kilometers instead of 2.6. The changes are slow, imperceptible on human timescales, but they're real. Beta's rotation is simpler. It's tidally locked. 1 rotation per orbit, 17.4 hours. The same face always points toward Alpha. The other face always points away. Tidal locking happens because of gravity gradients. Alpha's gravity is stronger on Beta's near side than on its far side. That difference creates torque. Over time, the torque slows Beta's rotation until it matches the orbital period. Earth's moon is tidally locked to Earth. That's why you always see the same face. Pluto and Charon are mutually tidally locked. They always show the same faces to each other. It's common in binary systems. From Beta's Alpha-facing side, Alpha would appear stationary in the sky. Enormous, unmoving. Only the slow rotation of Alpha beneath you once every 2.8 hours would mark time. From Beta's far side, you'd never see Alpha, just stars. Unchanging stars because Beta doesn't tumble. You'd see the sun rise and set once every 17.4 hours as Beta orbits, but Alpha would remain forever below the horizon. It's a strange geometry. 2 bodies locked in mutual orbit, neither fully free, neither fully bound. A waltz in slow motion. The binary system also precesses. The plane of Beta's orbit around Alpha rotates slowly over time, influenced by the sun's gravity. The precession period is about 80 years. Not that it matters much, there are no seasons on an asteroid, no equinoxes to mark. Just geometry changing in silence. Between the 2 visitors, the contrast in motion is absolute. 3I, Atlas hyperbolic escaping, tumbling out gassing, unpredictable in detail. 1999 KW4 elliptical returning, spinning tidally locked predictable for millennia. 1 is chaos constrained by gravity. 1 is order maintained by gravity. Both obey the same laws. Newton's laws, Kepler's laws. Einstein's corrections for space-time curvature, though those are tiny at these speeds and distances. But the outcomes are opposite. 1 leaves forever. 1 returns forever. You could watch 1999 KW4 for a lifetime and plot its orbit to within meters. You could predict where it will be in 100 years, 1,000 years, 10,000 years. Not perfectly, chaos creeps in, but well enough. You could watch 3I Atlas for a lifetime and never see it again. It will fade from view, fade from memory, fade from the sun's influence, and drift back into the dark. In 1,000 years, it will be light years away. In 1,000,000, it might pass near another star, or it might not. The uncertainty grows with distance. 1 is a clock, 1 is a traveler, and yet both are here now, moving through the same space at the same time. For a few months in 2024, their stories intersect. Not physically, they are millions of kilometers apart, but observationally. Telescopes watch both. Instruments measure both. 2 objects, 2 trajectories, 2 fates. Bound and unbound. Returning and departing. Motion is the default state of matter. But the kind of motion closed or open, repeating or singular, depends on speed and history. and the shape of space-time around you. 3I, Atlas moves fast enough to leave. 1999, KW4 doesn't. That's the only difference that matters, and it makes all the difference. One will drift until stars die. One will circle until planets fall. Both are just following lines through curved space, doing what gravity tells them, obeying mathematics that neither knows nor cares. But from here watching, you can see the poetry in the difference. The stranger and the neighbor, the comet and the asteroid, the one-time visitor and the regular guest. Motion written in numbers, fate written in curves. Surfaces remember. Every impact, every photon, every grain of dust that strikes a surface leaves a mark. Sometimes visible a crater, a scratch, a discoloration. Sometimes invisible a rearranged atom, a broken bond, a crystal turned to glass. Given enough time, a surface becomes a history book written in scars. 3I Atlas's surface is obscured, not physically hidden, we can see it through telescopes, but obscured by activity. The nucleus is wrapped in a coma, a cloud of gas and dust, tens of thousands of kilometers wide. The coma glows in reflected sunlight, but it also scatters light blurs. Details makes it hard to see the solid body beneath. What we know about the surface comes mostly from inference. Light curves tell us about shape. The way brightness varies suggests an elongated nucleus may be twice as long as it is wide. Spectroscopy tells us about composition ices mixed with dark carbonaceous dust. Thermal models tell us about temperature gradients, how heat penetrates, where it accumulates, where it escapes. The surface itself is probably layered. A crust of refractory materials, silicates, organics that don't sublimate easily, covering pockets of volatile ices beneath. When sunlight warms the surface, heat conducts inward, where the temperature reaches the sublimation point of water ice around 200 Kelvin. At low pressure, the ice turns directly to vapor. The vapor builds pressure beneath the crust. Eventually, the pressure exceeds the strength of the overlying material. The crust fractures. Gas escapes in a jet, a plume shooting outward at a few hundred meters per second, carrying dust with it. These jets are visible in images. Narrow streams of brightness extending from the nucleus, fading as the gas disperses. Some jets are steady, lasting hours or days. Others are sporadic, flaring and dying as cracks open and seal. The pattern of jets tells you about surface structure. If jets appear near the same longitude repeatedly, it suggests that region has thinner crust or richer ice deposits. If jets turn on and off with the comet's rotation, it suggests they're triggered by sunlight, active when facing the sun, dormant when in shadow. For 3I Atlas, the jet pattern isn't well resolved. The comet is faint, the coma is diffuse, and ground-based telescopes can only see so much. Hubble tried to image it in late 2024, but even Hubble's resolution, sharp enough to see craters on Pluto, struggles with a 500-meter object 150 million kilometers away. What we can infer is that the surface is heterogeneous. Some regions are active, some are dormant. The dormant regions might be mantled, covered in a thick layer of dust that insulates the ice beneath, preventing sublimation. Mantling happens when dust ejected in previous active periods falls back to the surface and accumulates. Over time, a comet's activity can decline as more of the surface becomes mantled. The ice is still there beneath meters of dust, but it can't escape. The comet becomes dormant, looks like an asteroid. Only detailed analysis detecting faint sublimation, measuring non-gravitational forces, reveals its true nature. 3I Atlas is still active, strongly active in fact. The coma is bright. The outgassing rate is high, hundreds of kilograms per second. That suggests large areas of exposed ice, thin crust, recent resurfacing. Recent meaning within the last few million years. Comets don't change fast, but they do change. Each time they pass near a star, they lose mass. Each orbit erodes the surface a little more. Over millions of orbits, a comet can lose kilometers of material. 3I Atlas has only passed one star recently, ours. Before that, it drifted in interstellar space for millions of years, frozen solid inactive. The last time it was warm enough to sublimate might have been during its departure from its parent star's system 4 million years ago, or more. So, the surface we see now might be ancient, preserved by cold, or it might be fresh exposed recently by a collision with an interstellar dust grain large enough to crack the crust and reveal the ice beneath. We don't know. We can only watch and guess. 1999 KWV4 surface is different. No coma, no outgassing, no jets. Just bare rock exposed to vacuum and radiation, and the slow rain of micrometeorites. The radar images from Arecibo show detail down to about 7.5 meters per pixel. That's sharp. Sharp enough to see individual boulders. Sharp enough to map the topography, the ridges, the valleys, the impact craters. Alpha's surface is rough. Boulders scattered across it like debris on a construction site. Some are 50 meters across, the size of a small office building. They're not evenly distributed. Clusters appear near the equatorial ridge, as if rocks rolled downhill and accumulated there. The ridge itself is striking. A band of elevated terrain running around the asteroid's equator, rising 50 to 100 meters above the average surface. It's not sharp, no cliffs, no peaks. Just a gradual swell, like a belt cinched too tight. The ridge probably formed when Alpha was spinning faster. Centrifugal force pushed material toward the equator. As the Yorp effect spun the asteroid up rocks, and regolith migrated equatorward, piling up in a bulge. When Beta separated, removing angular momentum, the spin slowed slightly, but the ridge remained. Craters are visible but not abundant. Maybe a dozen craters larger than 20 meters across. That's fewer than you'd expect on an ancient airless surface. The scarcity suggests resurfacing processes that erase or bury old craters. One resurfacing mechanism is seismic shaking. Asteroids don't have tectonic plates or volcanoes, but they do experience quakes. Each time 1999 KW4 passes near Earth, or another planet, tidal forces flex it slightly. The flexing is tiny millimeters maybe, but enough to shake loose material. Regolith on an asteroid behaves strangely in low gravity. A quake can make the surface ripple like liquid. Boulders can bounce, tumble, migrate. Over millions of years, quakes can smooth out rough terrain, fill in craters, redistribute material. Another mechanism is Yorp-induced landslides. As the rotation rate changes, the effective gravity at different latitudes changes. Material that was stable at one spin rate becomes unstable at another. Slopes that held firm start to slump. Regolith flows toward lower elevations, burying whatever was there before. The result is a surface that looks young, even if the asteroid is old. Fresh, even if nothing dramatic has happened recently. Between the boulders and ridges, the surface is covered in regolith, fine dust pulverized by billions of years of micrometeorite impacts. Each impact is tiny, a grain of sand moving at 20 kilometers per second, carrying kinetic energy but very little mass. The impact vaporizes the grain, and a small amount of surface material, the vapor condenses as microscopic beads of glass. Over time, the glass beads accumulate. The surface becomes a mix of rock fragments, mineral grains, and glass spherules, all ground down to powder, finer than flour. This is regolith. It's cohesionless. No water, no organic binders, nothing to hold it together, except weak electrostatic forces. If you walked on it hypothetically in a spacesuit in gravity so weak you'd weigh less than a coin, your boots would sink. Not deep. Maybe a few centimeters. The regolith would compress beneath your weight, then spring back when you lifted your foot like memory foam in extreme slow motion. Each step would raise a small cloud of dust. In Earth's atmosphere, dust falls. In vacuum, it doesn't. It follows ballistic arcs, like tiny bullets landing meters away. You'd be constantly surrounded by a halo of drifting particles glinting in sunlight. The regolith is also dark, space weathering darkened surfaces over time. Fresh rock newly exposed by a recent impact reflects maybe 20% of the light that hits it. Space-weathered rock reflects 5% or less. The darkening happens because solar wind and radiation break chemical bonds, freeing metal atoms from silicate minerals. The metal condenses into nanoscopic grains of iron. These grains absorb light efficiently. So, alpha's surface, which is mostly olivine and pyroxene minerals that are greenish or gray when fresh looks charcoal black. Dark as asphalt, darker in some places. Beta's surface is smoother, fewer boulders, fewer large craters. This makes sense if beta is made of material that lifted off alpha's surface. The material that escapes most easily is small regolith grains, pebbles. Large boulders stay put. So beta inherited the fine-grained fraction and alpha kept the coarse-grained. Beta's surface also shows evidence of mass wasting. Slopes facing alpha have shallow grooves, as if material has slid downhill toward the sub-alpha point, the spot on beta that always faces alpha. This might be caused by tidal forces. Alpha's gravity pulls slightly harder on beta's near side, creating a gradient that over time can move loose material. The far side of beta, the hemisphere that never sees alpha, is less well mapped. Radar imaging from Earth can only see the near side clearly. The far side is inferred from light curves and thermal models. It's probably similar, dark, dusty, cratered, but details remain uncertain. One interesting feature on alpha is a possible impact crater near the North Pole. It's subtle, a circular depression about 100 meters across, slightly deeper than the surrounding terrain. If it's an impact crater, it's young. Old craters get filled in by regolith migration. This one is still visible, which suggests it formed within the last few 100,000 years. Young, but not recent. Recent would be yesterday or last year. On an asteroid, recent means within the last orbit. This crater predates human civilization. Maybe predates modern humans entirely, but it's young compared to the asteroid's age. Impacts on asteroids are slower than you might think. The asteroid belt isn't crowded. Objects are separated by millions of kilometers. Collisions are rare. A typical asteroid might experience one significant impact, large enough to leave a crater every few million years. But smaller impacts are common. Sand grain-sized meteoroids hit constantly. Over 1 million years, they erode the surface at a rate of millimeters per million years. Slow, imperceptible on human timescales, but relentless. The surface of 1999 KW4 is old in the sense that it's been exposed to space for billions of years. But it's young in the sense that it's constantly being refreshed by impacts, by quakes, by the slow downhill creep of regolith under gravity so weak it barely deserves the name. 2 surfaces, 2 histories. 3I, Atlas. Active outgassing, cloaked in vapor, changing every day as ice sublimates and jets erupt. A surface in motion, breathing alive. In the chemical sense, if not the biological. 1999, KW4, dormant, silent, baked by sunlight and sand-blasted by dust, changing so slowly that 1,000 human lifetimes wouldn't see a difference. A surface in stasis, patient waiting. Both are shaped by their environments. 3I, Atlas by the warmth of the sun, brief but intense. 1999, KW4 by the cold mechanics of vacuum and time, both carry scars. Impacts, fractures, grooves, ridges. Each scar is a story, a moment when something changed. A grain of dust, a photon of light, a shift in temperature, a tremor in the rock. Surfaces remember, even when no one is watching, even when no one cares, even when the events happened millions of years ago and the witnesses are long gone. The surface remembers because matter has no choice. Every interaction leaves a trace. Every trace is permanent, or nearly so, in the absence of wind and water and biology to erase it. You could read these surfaces the way archaeologists read ruins. The boulders are artifacts. The craters are archives. The regolith is sediment layer upon layer, each grain a page in a book written over eons. We've only read the first few sentences. The rest is still out there waiting, silent, patient, holding its secrets in the shape of dust and stone. Light carries information. Every photon that leaves a surface tells you something about where it came from. The wavelength tells you about energy. The polarization tells you about surface texture. The spectrum tells you about composition. The timing tells you about rotation. Light is how we listen to things too far to touch. When astronomers pointed telescopes at 3i Atlas, they weren't just looking, they were listening, collecting photons, counting them, sorting them by color, measuring how the brightness changed over hours and days. Each photon is a messenger. It traveled from the sun to the comet, bounced off ice, or dust traveled to Earth, entered a telescope, struck a detector. The journey took about 16 minutes, 8 minutes from sun to comet. 8 minutes from comet to Earth, though the exact time varied as distances changed. The detector recorded the photon's arrival. One click, one data point. Millions of clicks build an image. Billions build a light curve, a spectrum, a map of how brightness varies across the coma. This is optical astronomy, passive. You wait for sunlight to illuminate the object, collect the reflected light, analyze it. You don't send anything, you just watch. But there's another way to listen, an active way. Radar astronomy sends its own signal, a pulse of radio waves tightly focused, aimed at the object. The pulse travels at the speed of light. When it hits the object, some of the energy scatters. A tiny fraction bounces back toward the transmitter. The transmitter becomes a receiver. It listens for the echo. The echo arrives delayed. The delay tells you distance. The frequency shift tells you velocity. The shape of the echo, how it's spread out in time and frequency, tells you about the object's size, shape, rotation, surface roughness. Radar sees through clouds, through comas, through anything transparent to radio waves. It sees the solid body underneath. For 3i Atlas, radar wasn't used. The comet was too faint too far, moving too fast. Radar works best on objects closer than a few million kilometers. 3i Atlas never came that close. Its perihelion was 57 million kilometers too distant for the radar telescopes on Earth to get a strong echo. So, we relied on light. Optical telescopes in Hawaii, Chile, Arizona. Infrared telescopes to measure heat. Ultraviolet telescopes to detect certain molecular emissions. Spectrographs to split the light into its component wavelengths. The light told us about the coma, water vapor, carbon dioxide, dust grains scattering sunlight. The brightness variations told us about the nucleus's rotation, 6.8 hours. The color told us the dust was reddish, organic, rich, similar to other comets. But there was another kind of listening, a different kind of signal. Breakthrough. Listen is a project that searches for techno-signatures, evidence of technology, of intelligence, of communication from other civilizations. It uses radio telescopes to scan the sky for signals that don't match natural processes. Narrow band transmissions, repeating pulses, patterns too regular to be random. In October 2024, Breakthrough Listen pointed its instruments at 3i Atlas, not because anyone thought the comet was artificial, but because it came from another star system. Because in principle, an interstellar object could carry a probe, could be transmitting. The odds were vanishingly small, but the cost of checking was low, a few hours of telescope time. And the potential payoff if something were found was infinite. They scanned from 1 to 12 gigahertz. That's the frequency range where Earth's atmosphere is transparent and where radio signals travel efficiently through space. They listened for narrow-band signals frequencies confined to a range smaller than a hertz, which would indicate an artificial origin. They found nothing. No signals. Just the faint hiss of thermal radiation, the comet's surface emitting radio waves. Because it's warm, the same way your body emits infrared, because you're warm. natural emissions, broadband, random. The absence of a signal is itself information. It tells you the comet isn't transmitting, at least not in the frequencies and directions monitored. It tells you it's probably just a comet. Ice and rock and organic molecules, not metal and circuits and intention. Still, the search was worth doing. Because you don't know until you check. Because the history of astronomy is full of surprises. Because Oumuamua, the first confirmed interstellar object, had such a strange shape and trajectory that serious scientists briefly entertained the possibility it might be artificial before better data ruled it out. 3 eyes, Atlas is less strange, more comet-like, but it's still an interstellar visitor, and visitors deserve attention. In 1999, KW4 received different attention, different signals. In May 2019, Arecibo transmitted. The radar pulse was generated by a klystron, a vacuum tube that converts electricity into microwaves. The pulse was shape-timed, sent into a waveguide routed to the feed horn at the focus of the dish, reflected off the 305-meter dish, focused into a beam and sent into space. The beam was narrow, about 2 arc minutes wide, roughly the width of a crayon held at arm's length. At a distance of 5.2 million kilometers, the beam spread to about 3,000 kilometers across, wider than the asteroid, but tightly focused compared to the vastness of space. The pulse hit 1999 kW by 4. The asteroid's surface reflected some of the energy. Not much rock is a poor reflector of radio waves. Only about 10% of the energy bounced back. The rest was absorbed, scattered, or transmitted through cracks and pores. The reflected energy spread out in all directions, but some came back toward Earth, toward Arecibo. The dish, now acting as a receiver, collected the returning photons. The echo was faint, billions of times weaker than the transmitted pulse, but detectable. Arecibo's receivers were sensitive. They could hear whispers. The round-trip time was about 34 seconds. That's 17 seconds for the pulse to reach the asteroid, 17 seconds for the echo to return. During those 34 seconds, the asteroid rotated slightly. Alpha spins once every 2.8 hours, so in 34 seconds it rotated about 3.4 degrees. That rotation smears the echo. Different parts of the surface are moving toward or away from Earth at slightly different velocities due to rotation. The Doppler shift varies across the surface. When you receive the echo, it's spread out in frequency, a range of Doppler shifts corresponding to different surface velocities. This is called delay Doppler imaging. You send many pulses over hours. Each pulse samples the asteroid at a slightly different rotation phase. You combine the echoes, sort them by delay, and Doppler shift, and build a 2-dimensional image. One axis is distance, the other is velocity. The images revealed boulders, craters, the equatorial ridge, the shape of alpha 2 lobes pressed together, the shape of beta, smaller, smoother, orbiting at 2.6 kilometers. The resolution was 7.5 meters per pixel, sharp enough to see a bus, sharp enough to count large rocks, sharp enough to measure the orbit of beta to within centimeters. Radar also told us about surface texture. Rough surfaces scatter radar more diffusely. Smooth surfaces reflect it more specularly. By measuring the polarization of the echo, how much is circularly polarized versus linearly polarized, you can infer the surface roughness at centimeter scales. 1999, KW4's surface is rough, dominated by regolith and boulders. No smooth plains, no flat surfaces. Just rocks and dust all the way down. The radar observations lasted several days. Arecibo transmitted for hours each day, collecting echoes, building up signal-to-noise ratio. The data filled hard drives. The analysis took months, but the result was worth it. A 3-dimensional model of a binary asteroid. Every ridge, every boulder, every crater mapped in radio waves. Goldstone Observatory in California also observed 1999 KW4. Goldstone has a 70-meter dish smaller than Arecibo's, but still capable. The two telescopes coordinated. Arecibo transmitted, Goldstone received. This bistatic radar setup increased sensitivity and allowed for different viewing angles. Together, the observations created the most detailed radar images of a binary asteroid ever made, until Arecibo collapsed in 2020, and the capability was lost. Now, Goldstone operates alone. The Green Bank Telescope in West Virginia can receive radar echoes, but it can't transmit. There are plans for new radar systems upgrades to Goldstone new dishes in other countries, but for now, the capability is diminished. When 1999 KW4 returns in 2036, we'll observe it. Goldstone will transmit. Green Bank will receive. Optical telescopes will watch. But the images won't be as sharp as 2019. The data won't be as rich. Arecibo's collapse was a loss. Not just of hardware, but of a way of seeing. A way of reaching out and touching objects millions of kilometers away, with pulses of light then listening for the echo. Two visitors, two ways of listening. For 3i, Atlas passive. Collect the sunlight it reflects. Measure the wavelengths. Infer the composition, the rotation, the activity. Listen to radio frequencies, just in case it whispers something unexpected. For 1999 KW4 active, send a pulse. Wait. Listen for the return. Measure the delay, the Doppler, the polarization. Build an image from echoes. One visitor we watched. One we touched at least with radio waves. Both answered. Not in words, not in messages, but in the language of photons, wavelength, intensity, polarization, timing. The language that predates words. The language that matter speaks when light asks questions. We asked, "What are you made of?" The light answered, "Ice rock, organics, metal." We asked, "How do you move?" The light answered, "Hyperbolic, elliptical spinning, locked." We asked, "What do you look like?" The light answered, "Jets, boulders, ridges, craters." We asked, "Are you alone?" The light answered, "Yes, no. It depends on what you mean by alone." The signals we receive are data, numbers, measurements, but they're also poetry. Photons that traveled across space to tell us about places we'll never visit, surfaces we'll never touch, histories we can only infer. Every photon is a gift, a small piece of truth wrapped in wavelength delivered across vacuum. We catch the photons, count them, decode them, turn them into images, spectra, numbers, understanding. And sometimes late at night when the telescopes are pointing at some faint speck of light millions of kilometers away, it feels less like observation and more like conversation. We send a signal, a question written in radio waves, or simply the act of looking. The universe sends a signal back, an answer written in light. The conversation is slow. The words are photons. The grammar is physics. But it's a conversation nonetheless. Between rocks and minds. Between matter and curiosity. Between what is and what wants to know. Distance changes meaning. A rock in your hand is geology. A rock orbiting the sun is astronomy. The same atoms, the same physics, but context transforms interpretation. 3i, Atlas in 1999, KW4 are both small bodies, both cold, both shaped by gravity and time. But the distances they have traveled, the context they have inhabited, make them fundamentally different in ways that matter. One has known only warmth interrupted by cold. One has known only cold interrupted by warmth. Niseen 99, KW4 formed in the solar system. It has orbited the sun for 4.5 billion years. Every 188 days it completes a loop. Perihelion at 0.23 AU, close enough to feel the sun's heat. Surface temperatures peak around 400 Kelvin in sunlit regions. That's hot enough to make water boil if there were any water. But there isn't. The asteroid is dry. It formed inside the snowline, where ices couldn't condense. It has never known liquid, never known atmosphere, just vacuum and radiation and the slow, steady warmth of the sun. The warmth is predictable. Every orbit the same pattern. Heating as it falls toward perihelion, cooling as it climbs toward aphelion. The temperature swings are large 400 Kelvin to 200 Kelvin, but they're regular, cyclic. The asteroid's minerals have adjusted. Thermal stresses have fractured the surface into regolith, but the fractures heal through sintering grains welding together slightly when heated, then cracking apart when cooled. Over billions of years, the asteroid has reached a kind of equilibrium. The surface erodes at a predictable rate. Impacts resupply the regolith. Quakes redistribute it. The system is stable. 3I Atlas has known no such stability. It formed around another star. Orbited that star, perhaps, for millions of years in the cold outer regions where ices dominate. Then it was ejected. The mechanisms aren't certain: a planetary migration, a stellar encounter, a slow accumulation of gravitational perturbations. But the result was expulsion. It left its star's warmth and entered interstellar space. The temperature dropped to 3 Kelvin, not 200 Kelvin, not 100 Kelvin, 3. The temperature of the cosmic microwave background, the faint afterglow of the Big Bang, the coldest natural temperature in the universe. At 3 Kelvin, molecular motion nearly stops. Chemical reactions effectively cease. Ice becomes harder than steel. The comet froze solid. Not just the surface, but the entire body down to the core if it has one. It stayed frozen for millions of years, drifting through the interstellar medium. No sunlight, no warmth. Just the faint pressure of starlight from distant suns, the occasional impact of a dust grain moving at tens of kilometers per second, the relentless bombardment of cosmic rays. Cosmic rays are high-energy particles, protons mostly accelerated to nearly the speed of light by supernova shock waves or active galactic nuclei. When a cosmic ray strikes a molecule, it breaks bonds, shatters the structure, creates free radicals, unstable fragments that react with whatever is nearby. At 3 Kelvin, those reactions are slow. The fragments don't have enough thermal energy to move far. But over millions of years, the surface chemistry changes, becomes darker, more carbon-rich. The process is called radiation processing. It's not unique to interstellar space. It happens on icy moons in the outer solar system too. But in interstellar space, there's no competing process to reverse it. No sublimation to refresh the surface. No impacts large enough to excavate fresh ice. The surface darkens, hardens, becomes a crust. Then in September 2024, 3I Atlas entered the solar system. The sun's light reached it. Slowly, degree by degree, the temperature rose. By the time it crossed Jupiter's orbit, the surface had warmed to maybe 100 Kelvin. Still cold by human standards, colder than the coldest place on Earth, but warm enough for the most volatile ices to begin sublimating. Carbon monoxide, maybe. Methane. By the time it reached 1 AU Earth's distance from the sun, the temperature had risen to 200 Kelvin. Water ice began to sublimate, slowly at first, then faster, as cracks opened and subsurface ices were exposed. At perihelion 0.38 AU, the sunlit surface reached 300 Kelvin or more, hot enough for vigorous outgassing, jets, coma. The transformation from dormant iceberg to active comet took less than 3 months. That's a temperature swing of 297 Kelvin, from 3 to 300, in a matter of weeks. For comparison, the most extreme temperature swing on Earth from the coldest Antarctic winter to the hottest Saharan summer is maybe 150 Kelvin, and that happens gradually over months, moderated by atmosphere and oceans. 3I Atlas had no atmosphere to moderate the transition, no ocean to store heat, just rock and ice warming in vacuum responding directly to sunlight. The thermal shock must have been immense, ice expanding as it warmed, rock contracting differently than ice. Stresses building, cracks propagating, the surface fracturing, maybe even fragmenting. Some comets don't survive perihelion. They break apart under thermal stress tidal forces, or the pressure of their own outgassing. 3I Atlas seems to have survived. It's still intact as of late 2024, but pieces might have separated, fragments too small to detect individually, but contributing to the coma. After perihelion, the temperature will drop, the comet will cool, the outgassing will slow, then stop. By the time it crosses Neptune's orbit outward, it will be frozen again. Not as cold as interstellar space, still within the sun's faint warmth, but cold enough that activity ceases. And then it will leave, exit the solar system, re-enter interstellar space, cool to 3 Kelvin, stay that way for millions of years, perhaps billions, perhaps forever. One visitor has known only cycles, one has known only extremes. 1999. KW4's orbit is predictable for thousands of years. Maybe not millions. Chaos creeps and planetary perturbations accumulate, but for the foreseeable future, it will return. Every 188 days. Perihelion aphelion, perihelion aphelion. A clock. 3I Atlas's trajectory is predictable in shape. Hyperbolic open escaping, but not in destination. It will leave the solar system on a path toward telescopium, but that's just a direction in the sky. There's no star it's aimed at, no target, just empty space. In a million years, it might pass within a light year of another star. Or it might not. The galaxy is large, stars are sparse. The odds of a close encounter are low. But even if it does pass near another star, it won't be captured. Its velocity is too high. It will swing past warm, briefly cool again, and continue. A perpetual wanderer. 1999. KW4 has a future. Chaotic, uncertain, but bounded. It will orbit the sun until something disrupts it. An impact. An ejection by Jupiter. A slow spiral into the sun due to the Yorp effect or tidal friction. But those events are millions or billions of years away. 3I Atlas has no future in the solar system. It's already leaving. By 2026, it will be beyond Neptune. By 2030, beyond the Kuiper Belt. By 2050, beyond the heliopause. After that, it's gone. The timescales are different too. 1999 KW4's binary configuration is young, maybe a million years old. Beta separated from alpha recently, cosmically speaking. The system is still evolving. Tidal forces are slowing alpha's rotation, pushing beta's orbit outward. In another million years, the configuration might be different. But the asteroid itself is old. 4.5 billion years. It has orbited the sun for the entire history of the solar system. It was there when Earth formed, when life began, when dinosaurs walked, when humans looked up and wondered about the lights in the sky. 3I Atlas is also 4.5 billion years old, give or take. But it hasn't been here. It spent its lifetime elsewhere, around another star, in interstellar space. It only arrived recently a few months ago from our perspective. It's a newcomer, a stranger. It doesn't know the sun the way 1999 KW4 does. It doesn't know Earth-Jupiter, the architecture of the inner planets. It's passing through a system it has no history with. One visitor is a resident, one is a tourist. Residents know the neighborhood. They've seen the seasons change, the neighbors come and go. They've adapted, found equilibrium, made a home in whatever sense a rock can make a home. Tourists pass through. They see the sights. They don't stay long enough to understand the local rhythms. They leave before they've learned the names. There's no value judgment in this. Residents aren't better than tourists. Tourists aren't more interesting than residents. They're just different. Different time scales, different relationships to place. But the difference shapes what we can learn from them. From 1999 KW4, we learn about stability, about how binary systems form and evolve, about how asteroids survive billions of years of impacts and radiation, about the inner solar system's history, what it was like when Earth was young, what the building blocks of planets looked like before they assembled. From 3I Atlas, we learn about diversity, about what other stellar systems produce, about the chemistry of cold molecular clouds light years away. about the journey through interstellar space, what changes, what stays the same, what it means to cross the void between stars. Both lessons matter. One tells us about home, one tells us about everywhere else. Together, they tell us something deeper, that the universe makes rocks the same way everywhere. That gravity and temperature and time follow the same rules whether you're orbiting our sun or another. That chemistry is universal, that the difference between a stranger and a neighbor is mostly history and chance. If 3I Atlas had formed in our solar system and 1999 KW4 had formed around another star, their roles would be reversed. The stranger would be the neighbor would be the stranger, but they didn't. So here we are, watching one leave, watching one return, learning from both. The contrast isn't about which is better, more important, more interesting. It's about completeness. You need both to see the whole picture. The cycles and the extremes, the familiar and the foreign, the bound and the unbound. Two visitors, two stories, two ways of being a rock in space. One remembers a sun we'll never see. One remembers only hours. One will drift until stars burn out. One will circle until planets fall. And for a brief moment in 2024, their stories intersected. Not because they meant to, not because they knew we were watching, just because space is large and orbits are math, and sometimes by coincidence, two rocks find themselves in the same volume of space at the same time. We call it chance. The universe calls it nothing. It doesn't call, it just is. But we're here, watching, measuring, learning, asking what it means that one came and one stayed. Maybe it means nothing. Maybe rocks are just rocks. Or maybe meaning is something we add, something we find when we pay attention, when we notice the differences, when we ask why. Knowledge accumulates in layers. First you observe, then you measure, then you model, then you understand or think you do, until the next observation forces you to revise. Science is a conversation between expectation and evidence. Sometimes evidence wins. Sometimes expectation was closer than you thought. Mostly the truth is more complicated than either. 3I Atlas teaches us about interstellar chemistry. Before it arrived, we had theories, models of how molecules form in cold molecular clouds, how ices condense in protoplanetary disks, how radiation alters surfaces during the journey through interstellar space. The models predicted certain compositions: water, carbon dioxide, simple organics. The same molecules we see in solar system comets because the chemistry should be universal. Carbon bonds with hydrogen under cold conditions, the same way everywhere. Then we measured 3I Atlas's spectrum. Water, yes. Carbon dioxide, yes. Hydrogen, cyanide, methanol, the expected organics. The models were right, but the isotope ratios were slightly off. The deuterium to hydrogen ratio, higher than Earth's oceans, lower than some solar system comets. The carbon-13 to carbon-12 ratio, different enough to suggest formation temperatures a few degrees colder than our own comet-forming regions. Small differences. Within error bars almost, but real. What does that teach us? That molecular clouds aren't uniform. That the temperature and density in one star's protoplanetary disk differ slightly from another's. That chemistry is universal, but conditions vary. It's a humbling lesson. We knew chemistry was universal. We just didn't know how sensitive it was to small variations in environment. Now we do. Because 3I Atlas carried a sample from another system, preserved by cold delivered to our instruments. Panspermia is an old idea. The hypothesis that life's building blocks, or even life itself, can travel between stars, carried on comets, asteroids, dust grains. Ejected from one system, drifting through space, landing on another world. It's speculative. No confirmed cases, no unambiguous evidence. But 3I Atlas makes it slightly less speculative. It carries organic molecules, not life, not even amino acids as far as we can tell, but the precursors. Hydrogen cyanide polymerizes into adenine under the right conditions. Formaldehyde and ammonia can form ribose, a sugar in RNA. The ingredients are there. If a comet like 3I Atlas could deliver those ingredients to a young planet, fall into the atmosphere, burn up, scatter organic molecules across the surface, it might contribute to the chemical environment where life begins. Earth might have received such deliveries. Early in its history, before life arose, comets and asteroids bombarded the surface. Some carried water, some carried organics. We don't know how much of Earth's water and carbon came from space and how much was here from the beginning. But comets contributed. Isotope studies suggest it. 3I Atlas reminds us that delivery can happen across interstellar distances, not just within a solar system, but between them. The timescales are enormous, millions of years in transit, but time doesn't destroy ice. It just waits. Could life itself travel this way? Microbes frozen in ice surviving cosmic ray bombardment, arriving intact on another world? Probably not. Cosmic rays break molecules. DNA is fragile. Even extremophiles, organisms that survive radiation and cold on Earth, struggle against millions of years of high-energy proton bombardment. But probably isn't never. And the question is worth asking. 3I Atlas doesn't answer it. It just reminds us the question exists. 1999, KW4 teaches different lessons. Binary asteroids are common. About 15% of near-Earth asteroids are binaries. We've found hundreds. But we don't fully understand how they form. The Yorp effect is part of the story. Sunlight spins up an asteroid until material lifts off the equator. The material coalesces into a moonlet. The moonlet drifts outward to a stable orbit. Simple in principle, but the details are messy. Not every asteroid spins fast enough. Not every fast-spinning asteroid sheds material. The strength of the material matters. Rubble piles behave differently than solid rock. The shape matters. Irregular bodies spin up faster. The spin axis matters. Obliquity affects how efficiently Yorp torques the body. 1999 KW4 is a case study, a textbook example. Alpha spins fast 2.8 hours. Beta orbits at 2.6 kilometers. The system is stable, tidally locked. The ages and configurations match Yorp predictions. But studying one system isn't enough. You need dozens, hundreds to test the models, to see which parameters matter most, to understand why some asteroids become binaries and others don't. Every radar observation adds data. Every light curve adds constraints. Slowly the picture sharpens. And the lesson is, complexity hides in details. You can't predict everything from first principles. You need observations, measurements, real data from real objects. Binary formation also teaches us about planetary defense. If an asteroid is heading toward Earth, and it's a binary, the deflection strategy changes. You can't just push the primary, you have to account for the moonlet. If you nudge the primary, the moonlet's orbit changes. Tidal forces might destabilize the system. The moonlet might separate, creating two threats instead of one. This hasn't happened yet. No binary asteroid has threatened Earth, but 15% of near-Earth asteroids are binaries. Someday one might. And when it does, we'll need to know how to deflect it safely. 1999, KW4 is a laboratory, a natural experiment we can observe, model, test our understanding against. The better we understand binary dynamics, the better prepared we are. The lesson isn't just about defense, it's about preparedness, about learning from objects that aren't threats today, so we're ready if they or others like them become threats tomorrow. Both visitors teach us about time. 3I Atlas measures time in light years. The distance it traveled from its parent star to ours is measured in years light takes to cross. 4 million years in transit, maybe more. That's longer than the genus Homo has existed, longer than most species survive, longer than mountains stand. And yet, in cosmic terms, it's brief. The galaxy is 13 billion years old. 4 million years is a blink, less than 1,000th of galactic history. 1999 KW4 measures time in orbits. It has completed 8.7 billion orbits around the Sun since the solar system formed. Each orbit is 188 days. If you stack those orbits end to end, they'd stretch across timescales incomprehensible to human minds. But each orbit is identical, or nearly so. The same perihelion, the same aphelion. Variations of a few kilometers, a few hours, but fundamentally the same pattern. Repetition on a scale that dwarfs human repetition. We think of time as linear, past, present, future, a line extending from birth to death. But these objects teach us time is also cyclic. Orbital periods, rotation periods, thermal cycles, patterns repeating until something breaks them. And time is also patient. Millions of years between events, billions of orbits accumulating changes too slow to perceive in a human lifetime. The human mind isn't built for these timescales. We think in days, years, decades, maybe centuries if we stretch, but millions, billions. The numbers are easy to say. The reality is impossible to grasp. So we use metaphors, calendars compressed into seconds, histories condensed into paragraphs, trying to fit cosmic time into human comprehension. The lesson both visitors teach is, time is larger than you, and smaller. It contains eons and instants. It erases and preserves. It's the medium through which everything changes, and the reason some things stay the same. There's also a lesson about rarity and ubiquity. Interstellar objects are rare. We've confirmed 5. One-eye Oumuamua, Two-eye Borisov, Three-eye Atlas. 2 others detected but less well studied. 5 in a decade of intensive searching. But estimates suggest 1 or 2 pass through the inner solar system every year. Most go unnoticed. Too faint wrong angle, no telescope pointed the right direction. So, they're rare in the sense that we rarely see them, but ubiquitous in the sense that they're always passing through invisible, unobserved. Binary asteroids are ubiquitous. 15% of near-Earth asteroids. Thousands in the main belt. Common enough that we don't name them all individually. They're catalog studied, but not special. Yet, each one is unique. Different mass ratio, different separation, different orbital inclination. No 2 binaries are identical. So, they're common in category, but rare in detail. The lesson rarity and ubiquity are context-dependent. What you're looking for. How you define the category. Whether you care about the class or the individual. Three-eye Atlas is one of billions of interstellar comets drifting through the galaxy, ubiquitous cosmically. But it's the only interstellar comet we observed in October 2024, rare temporally. 1999 KW4 is one of thousands of binary asteroids, common statistically. But it's the only binary we observed with Arecibo radar at 7.5 meter resolution in May 2019. Rare historically. Perspective changes what you see. Both visitors also teach us humility. We don't know where Three-eye Atlas came from. We know the direction Lyra, but not the star. Too many candidates, too faint to identify from this distance. We don't know where it's going. We know the direction Telescopium, but not the destination. Empty space, probably. Maybe a star in a million years. Maybe nothing. We don't know how 1999 KW4 will end. Collision ejection, spiral into the sun. The orbit is chaotic on million-year timescales. We can predict the next century. The next million years is guesswork. Science gives us tools, equations, models, instruments. But it doesn't give us omniscience. There are limits, some built into the physics chaos theory, uncertainty principles, some built into our resources telescope, time, funding, human attention. The lesson is, knowledge is partial, always. Every answer opens new questions. Every measurement has error bars. Every model has assumptions. But partial knowledge is still knowledge. It's better than guessing, better than ignorance. We know more about these 2 visitors than we did a year ago. We know their compositions, orbit surfaces, histories. We know what they teach us about chemistry, dynamics, time, rarity. We don't know everything. We never will. But we know enough to ask better questions, to design better instruments, to look for the next visitor and learn from it too. That's the deepest lesson. Not what 3i Atlas and 1999 KW4 are, but what they make possible. They make curiosity possible, wonder, the recognition that the universe is larger and stranger and more beautiful than any single mind can hold. They make science possible, the slow, patient accumulation of observations that builds into understanding. They make meaning possible, not because rocks inherently mean something, but because we're here, watching, asking, trying to understand. And in that trying, we find something worth doing. Humans have always looked up, before telescopes, before writing, before language had words for star or sky or distance. We looked up and wondered. The wondering is older than civilization, older than agriculture. Petroglyphs in caves show constellations carved by hands that never held metal tools, bones notched with lunar cycles, stone circles aligned to solstices. The tools change, the technology improves, but the impulse, the looking, the wondering remains constant. Why? Why do we spend billions building telescopes to see things we can never touch? Why do we bounce radio waves off asteroids millions of kilometers away? Why do we care about a comet that passed through for a few months and will never return? The practical answers are easy. Planetary defense. We need to track near-Earth objects in case one threatens us. Resource assessment: asteroids contain metals, water, materials we might use. Scientific knowledge understanding the solar system helps us understand Earth. All true, all useful, but incomplete, because humans have looked up for 200,000 years, and for most of that time the sky posed no threat we could defend against, contained no resources we could mine, offered no knowledge with practical application. We looked anyway. There's something deeper, something harder to name. Maybe it's loneliness. Earth is the only place we know of where life exists. We've searched, sent probes to Mars, Europa, Titan, scanned the sky for radio signals, found nothing. No microbes, no messages, no evidence we're not alone. The universe is large, billions of galaxies, trillions of stars, more planets than we can count. Somewhere, probably life exists, maybe many somewheres, but we haven't found it. So we study rocks, comets, asteroids, dust grains, things that aren't alive but that come from other places, things that carry information about what's out there. 3i Atlas came from another star. It carries chemistry from another system. Not life, but the building blocks. The same molecules that under the right conditions might assemble into something that grows, replicates, evolves. Studying it is a way of asking, are we alone? Not directly. The comet can't answer, but it carries clues about how common organic molecules are, about how easily they travel between stars, about whether the chemistry of life is rare or ubiquitous. We don't know yet, but every interstellar visitor adds data, narrows the uncertainty. Maybe the question isn't loneliness, maybe it's belonging. We came from the universe, carbon forged in stars, oxygen from supernova explosions, hydrogen from the Big Bang itself. Every atom in your body is older than Earth, older than the sun. You are made of star stuff. Carl Sagan said it. Others before him sensed it. It's not poetry, it's physics. But knowing it intellectually and feeling it viscerally are different. When you look at 3i Atlas, a comet made of the same atoms as you born around another star, traveling for millions of years to briefly warm itself by our sun, you feel the connection. Not abstractly, concretely. That comet is your distant cousin, made in the same kind of stellar nursery, shaped by the same physics, subject to the same laws of chemistry and thermodynamics and entropy. It's not alive, it doesn't know you exist, but it's kin nonetheless. And 1999 KW4, a rock that's been here as long as Earth. that orbited the sun before oceans existed, before life began, before anything on this planet could look up and wonder. It was here first. We're the newcomers, and yet we name it, study it, treat it as object rather than elder. But maybe there's respect in that study, a way of honoring the long history, of saying, you were here before us, you'll be here after. We want to know your story. Maybe the question is curiosity itself, not curiosity in the trivial sense, idle wondering, casual interest, but curiosity as existential drive, the need to understand, to push against the boundaries of ignorance. Humans are pattern-seeking animals. We see faces in clouds, constellations in random stars, stories in everything. It's hardwired, survival trait maybe, or accident of neural architecture. But it's also curse and gift. Curse because we see patterns that aren't there, conspiracy where there's coincidence, design where there's randomness. Gift because we see patterns that are there, laws, regularities, the deep structure of reality. Science is formalized curiosity, a method for testing whether the patterns we see are real, for asking, is this pattern in my head or in the world? When we study 3I Atlas in 1999, KW4 were asking that question. Do they follow the patterns we predict? Do their orbits match Kepler's laws? Do their compositions fit? Models of planetary formation? Mostly yes. Sometimes with small surprises. The surprises refine the models sharpen the questions guide the next observations. It's a loop. Curiosity drives observation. Observation answers some questions and raises others. The new questions drive more observation. The loop doesn't close, it spirals, each turn broader than the last, encompassing more, understanding deeper. Maybe that's the answer, not a single reason we look up, but a constellation of reasons. Survival, knowing what might fall from the sky. Resource, knowing what we might use. Knowledge, knowing how things work. Connection, knowing where we came from. Humility, knowing how small we are. Wonder, knowing how much there is we don't know. All of these, none fully sufficient alone. Together, something closer to complete. But maybe there's one more reason, the hardest to articulate. Maybe we look up because we can. Because humans uniquely, as far as we know, can ask why, can build telescopes, can do math, can turn photons into understanding. It's a gift, that capacity, not in the sense of divine bestowal, in the sense of lottery win, evolutionary accident, neurons arranged just so, vocal cords that can form arbitrary sounds, hands that can manipulate tools. Most species can't do what we do. Most matter can't. Rocks sit, stars burn, gas expands. None of them wonder. We wonder. And because we can, maybe we should. Maybe the wondering is its own justification. Not because it serves survival or builds wealth or answers ultimate questions, but because it's what makes us human. To look at a comet from another star and ask where it came from. To measure an asteroid's spin and infer a billion-year history. To care about rocks we'll never touch. That's uniquely human. Strange when you think about it. Impractical. Inefficient. No other species spends resources on such things. But we do, and maybe that's enough. 2 visitors, 2 rocks, one from far, one from near. Neither knows we exist, neither cares, but we care. We named them, measured them, wrote papers, built models, argued about interpretations, allocated telescope time, funded missions, devoted careers, all for what? Knowledge, yes, but more than that, for the satisfaction of understanding, for the beauty of the patterns, for the connection to something larger, for the humility of confronting how much we don't know, for the wonder of living in a universe where rocks carry stories, and light carries information, and time carries everything forward. The question, why do we listen to rocks drifting through darkness, doesn't have one answer. It has as many answers as there are people asking. Some listen because they're scientists. It's their job, their training, their contribution to the slow accumulation of knowledge. Some listen because they're human, because curiosity itches and ignorance aches and understanding soothes. Some listen because the night sky is beautiful and they want to know what they're looking at. Some listen because they're lonely and the stars are company. Some listen because rocks from space are cool and telescopes are impressive, and who wouldn't want to bounce radar off an asteroid? All valid, all true. But underneath, maybe there's a common thread. We listen because we're here, because we evolved eyes that see light and brains that find patterns and hands that build instruments. Because we exist in a universe that allows complexity permits, life makes minds possible. We listen because existence itself is improbable and brief and precious. And listening, observing, measuring, understanding is a way of honoring that. Not worshiping, not glorifying, just acknowledging. We're here. The universe is here. For a little while we overlap. And in that overlap, we look, we measure, we wonder, we ask. Not because rocks will answer, but because asking is what we do. It's what makes the brief flicker of consciousness meaningful, what transforms atoms into awareness, what turns matter into minds that can ask why. 3I. Ace. Atlas doesn't know it taught us about interstellar chemistry. 1999, KW4 doesn't know it taught us about binary dynamics. They're just rocks, following orbits, obeying physics, indifferent to observation. But we're not indifferent. We care. We pay attention. We find meaning in their motion and composition and history. That meaning isn't in the rocks. It's in us, in the caring, in the attention, in the slow, patient work of turning observations into understanding. Maybe that's the deepest answer to the question. We listen to rocks drifting through darkness because we're the part of the universe that learned to listen. And having learned, we can't help but continue. The sky is darker now than when we began, not because stars have dimmed, because your eyes have adjusted, pupils wide, retinas sensitive, the faint lights you couldn't see an hour ago. Satellites distant galaxies, the zodiacal glow are visible now if you know where to look. Adaptation takes time, so does understanding. 3I Atlas is leaving. Right now as you breathe, it's climbing out of the sun's gravity well, moving at 26 kilometers per second, slower than it was at perihelion, but still fast enough to escape. By early 2026, it will cross Neptune's orbit. The sun will be a bright star behind it, no longer a disk. The warmth will fade, surface temperature dropping toward the cold it knew before, not quite 3 Kelvin, but close enough. The outgassing will stop. The coma will dissipate. The jets will fall silent. What remains is a dark nucleus tumbling slowly invisible to our telescopes, carrying its cargo of ice and organics back into the space between stars. It won't be alone. Interstellar space isn't empty. Hydrogen atoms, dust grains, other ejected comets, other wanderers. But it will be isolated. Light years from the nearest star. Decades of travel before starlight becomes warm enough to notice. The journey continues. No destination, no purpose. Just motion, obeying mathematics, tracing a hyperbola that never closes. Somewhere millions of years from now, it might warm again. Another star, another perihelion, another brief awakening before the cold returns. Or it might drift forever, growing colder, darker, more altered by radiation, until the galaxy itself changes shape and the stars it passes are not the stars we see tonight. We'll never know. The comet is beyond our reach, beyond our instruments, beyond the span of human attention, which is brief and easily distracted. But it was here. For a few months in 2024, we saw it, measured it, learned from it. That moment is over. The comet doesn't know, doesn't care. It's just ice and rock following the only path gravity allows. But we know. We were here when it passed. We pointed our telescopes, collected photons, turned light into data into understanding. That understanding remains, even as the comet fades, even as we forget its catalog number, misplace the images, move on to other questions. The knowledge stays, stored in papers, databases, minds, part of the slow accumulation that builds over centuries into something resembling wisdom. 1999, KW4 is easier to hold on to. It's out there now somewhere in its ellipse, perhaps near aphelion 1.17 AU from the sun, moving slowly, cooling in shadow, or perhaps falling back toward perihelion, warming, spinning beta, orbiting faithfully as it has for 100,000 years. We can calculate exactly where it is. The orbital elements are known to high precision. Plug in the date, run the equations, and you'll get coordinates accurate to within kilometers. But we're not tracking it. Not right now. There are other asteroids to observe, other comets, other priorities. It will return. Not to the same place orbits precess. Nothing repeats exactly, but close enough. In 2036, it will swing near Earth again. Not as close as 2019, but visible, observable. Goldstone will be ready. Greenbank maybe. Whatever telescopes we've built by then. The observations will add to the 2019 dataset, refine the models, test predictions, measure how much the orbit has changed in 17 years. Then it will leave, return again in another 188 days. Again. As long as the sun burns or until something disrupts it, a collision, an ejection, a slow spiral inward. Someday something will end the pattern, but not soon, not in human time scales. For now, it orbits, predictable, patient, a clock ticking in the dark. 2 visitors, 2 fates, one gone, one returning. Both indifferent to us, both shaped by forces older and larger than minds. We watched them, named them, tried to understand. We asked where they came from, what they're made of, how they move, what they remember. The answers weren't complete. They never are. Every observation raises new questions. Every measurement has error bars. But the asking matters. Not because rocks need to be understood. They don't. They exist whether we notice or not. But because we need to ask. Because curiosity is the thing that separates awareness from mere existence. Because understanding, even partial, even uncertain, gives shape to the chaos. The universe is large, indifferent, cold in most places, empty in most places, hostile to complexity. And yet, here on this planet in this moment, complexity arose. Molecules organized into cells, cells into organisms, organisms into minds, minds that can look up, wonder, ask why. That's improbable, maybe unique, certainly rare. For a brief window, a few million years perhaps, in a universe billions of years old, matter on this planet is awake, watching, learning. The window will close, stars burn out, planets cool, civilizations rise and fall and leave no trace. But right now, the window is open, and through it we see 2 rocks, one from far, one from near, both drifting through the dark, carrying stories written in chemistry and motion. We read what we can, we learn what we're able, we share the knowledge with others who care. That's enough. Not because it solves everything, not because it answers the deepest questions, not because it makes us immortal or the universe kind, but because it's what we can do, what we choose to do, what gives meaning to the brief time we're here. Someday no one will remember 3i Atlas. The papers will decay, the databases will corrupt, the knowledge will fade. Someday 1999 KW4 will collide with something or be ejected or spiral into the sun, and the binary waltz will end. Someday the sun will exhaust its hydrogen, expand into a red giant, engulf the inner planets, scatter their atoms into space. Everything ends, stars, worlds, species. Knowing this doesn't make it easier, just true. But endings don't erase what was. For a few months in 2024, A comet from another star passed through our sky. We saw it. It mattered. For billions of years, an asteroid has orbited the sun with a companion. We measured it. It mattered. For a few million years past and future combined, humans have looked up and wondered. We asked. It mattered. Mattering doesn't require permanence. It just requires presence, attention, care. We were here. We paid attention. We cared. The rocks don't know. The universe doesn't notice. But we know. We notice. And maybe that's the only kind of mattering there is. The night is quiet now. The stars are steady. Somewhere too faint to see two visitors continue their journeys. One toward cold and distance and silence. One in circles returning faithful as tides. Both doing what rocks do, following orbits, obeying physics, indifferent and ancient and real. You're still here, still listening, still breathing the same air you breathed when we started. But something has shifted, not outside, inside, in the knowing, in the connection between you and those distant rocks, between matter and mind, between what is and what notices. You know their stories now, not completely, but enough. Enough to see them not as dots of light, but as places, as histories, as kin. Enough to feel maybe a little less alone, a little more connected to the vastness. Sleep well, dream gently, and when you look up tomorrow night or next week or next year, remember the rocks are still out there, still moving, still carrying their stories through the dark, and you're still here, still watching, still part of the universe that learned to wonder. Good night.